So those are the announcements I have. And with that, it's my pleasure to welcome Lieven Vandersypen to give the morning tutorial. He's from TU Delft and QuTech, and he will tell us about quantum computing with spins, past, present, and future. Take it away, Lieven.
Well, thanks, John. Thanks for the invitation to you, Michiel, and all the other organizers, and for putting together this really very well organized conference. Glad to be here, first time in Rochester. Since it's a tutorial, indeed, I decided to take a little bit of a broader view. I will, of course, not resist the temptation to speak about our latest results, but I wanted to start with a bit of a broader perspective. And I also chose a title that's a bit broader, which is, thinking about quantum computing based on spins, and in particular, spin 1/2. There is nothing more prototypical as a qubit than a spin 1/2, after all. The block sphere picture, it kind of maps 1-to-1. You could say, well, any qubit maps 1-to-1, but in this case, it's really very physical. We can think of the expectation value of the spin pointing in a certain direction as corresponding to the point on the block sphere that the qubit is in. And I actually like that. Over breakfast with some people, we were talking about intuition. This is, for me, really intuitive. I can see the spins go around in my head. They are spinning in my head. And I actually like this. I started working on quantum computing based on spins for my PhD at Stanford. And here you see a picture from 25 years ago, where I was working together with Matthias Steffen, also a PhD student at Stanford, started a year after me, in Ike Chuang's lab at IBM Almaden. We could do our research work there. And we were using the spins of nuclears, of atomic nuclei in a molecule, specially designed and synthesized molecules like this one here. It has a backbone of 4 carbons. The inner 2 were carbon-13. So these have a spin 1/2. These are non-magnetic. And then you have 5 fluorine spin 1/2s. And so these were 7 qubits in this molecule. In practice, the signal from a single nuclear spin, certainly 25 years ago, was far too weak to be detected. And so what we did was use conventional commercial liquid state NMR methods. So there were billions of copies, Avogadro's number of copies of this molecule in a liquid solution, and you place it in an NMR magnet. The frequencies are in the hundreds of megahertz, so it's RF, which is quite slow and convenient in terms of technology. The couplings between the spins in this molecule were between 2 and 200 hertz. Dephasing times were very long, orders of seconds. So everything is on long time scales, which made it accessible. And of course, we were benefiting from decades of development in liquid state NMR by chemists and biologists who were interested in probing molecules. So using these methods, we applied a sequence of more than 300 RF pulses to these 5 spins selectively. Each of them had a carefully tailored profile in amplitude and phase to take care of frequency selectivity, but also various levels of crosstalk and various levels of sophistication in dealing and compensating for the crosstalk. And in doing so, we took the molecule through the steps of Shor's factoring algorithm. And we were very pleased that from the output spectra, which you see on the right, we could work back that the factors of 15 are 3 and 5. So that was the crown on my PhD, 4 years of hard work. 15 is 3 and 5. I like this experiment because, I'm attached to it, but apart from that, I think it's a good message. It conveys, on the one hand, that, we can test these algorithms and they behave as expected in an experimental setting. But also, of course, it's kind of something to laugh at, right? We didn't need a quantum computer to solve this problem. I think that is, in a sense, still the state of the field 25 years later, that although, the things we can do now are much more sophisticated, we're still not, for instance, factoring very large numbers and cracking RSA. Before moving on, I want to pause. This conference is dedicated to Joe Eberly. Actually, I didn't know Joe, but I did know very well, or quite well, Ray Flam. And on my way here, I learned that he also passed away just a few days ago. This is just really sad. He was a very energetic, fun, creative guy, and I have especially good recollections of lengthy discussions at the workshop in Aspen, where in the course of the discussion, I got some ideas for how to prepare the initial state of the nuclear spin. So what I didn't emphasize is these are room temperature experiments, and there's a big problem scaling this up. Even though we could move quickly, we couldn't go much further because of the state preparation. There is an exponential cost in the state preparation. But I realized how to do this more efficiently, and in practice it meant that all the all the experiments came in a factor 5 faster than without this discussion with Ray Laflamme. So I really owe him for finding the factor of 15 in a way. It's very sad. Now, like I mentioned, it's not a scalable approach, mostly because of the state preparation of the nuclear spins at room temperature. And so after finishing my PhD, I wanted to continue with quantum computing and continue with spins because I love the field and I love the intuition of spins. But then moved to systems where instead of having an ensemble, you work with individual spins, and then instead of room temperature, go to cryogenic conditions where you can really prepare your states your spins in a pure state. And several methods are explored around the world for doing this, such as nuclear spins surrounding the electron spin attached to a nitrogen vacancy center in diamond. There are other color centers that are used for this, and we'll hear more about it throughout the conference. In a moment, you'll hear from Michel Simmons about amazing work using phosphorus spins or electrons bound to a phosphorus impurity in silicon and using both the nucleus and the electronic spin as qubits. And finally, the possibility of confining electrons in nanoscale devices that we call quantum dots and using the spin of the electron as a quantum bit. And I have to admit that since 2001 been my favorite approach, and I've been working on it for all these years, and I'll tell you a little bit more about that. The way that we confine our spins is basically a combination of two things. First, we start from a heterostructure, so a layered structure of semiconductors, in this case grown by chemical vapor deposition, on top of a silicon substrate, and then you gradually increase the germanium composition, and then abruptly you have a thin, let's say 6-8 nanometer thick layer of silicon, and then another 30 or so silicon germanium, and then you get the gate stack. Because of the band offsets, the electrons, when you accumulate them using the gate voltage, so you apply a positive voltage to pull in carriers underneath the gate, like in a transistor, they will all move and reside in the quantum well, in the silicon here. The silicon, by the way, is not standard silicon, it's isotopically enriched, silicon-28, and I'll comment more on that in a moment. Now, if we don't have a single gate, but we have a number of gates kind of side by side, what we can do is dial in the voltages such that we construct a potential landscape where below here, there are lots of electrons. All the states are filled up until the Fermi energy over here, so that's a Fermi C. Then you have a potential barrier. And then between this barrier and the next, there is a small space, think of a few tens of nanometers, where the voltage that we apply is such that we pull in just one electron. And because of the low temperatures and because of the Coulomb repulsion between the charges, that's a very stable condition. So if you come back to our lab the next day, the electron will still be there, and next month also, and next year also, as long as your fridge stays cold, basically. So that's a very stable condition. And then the spin of that electron will be the quantum dot. The quantum bit. The quantum dot is what we call this small, nanoscale space where the electron is confined. You can then imagine that you make patterns where there are many of these gates side by side, so you can have several electron spins, several qubits next to each other. You could also imagine doing this in 2 dimensions, and in this way build up arrays. And then what's important is that the barrier that separates the electrons can be controlled in situ with gate voltages. That's important for the 2-qubit gate that I'll come back to in a moment. By the way, it's a tutorial, and if there are questions along the way, I certainly welcome them, so don't hesitate to ask. So then, coming from NMR, the natural thing is try to manipulate your spin using magnetic resonance, and so that's what we did. And in this first experiment, it was actually pretty crude, but it worked, an experiment done by PhD student Frank Coppens. So we had, on top of the quantum dot gates, which you see a little bit hidden here, the gates that confine the electron. We had this sort of coplanar strip line, which was shorted together at the end, and we passed an oscillating current through it. And if that oscillating current was applied at the right frequency, it would be resonant with the spin precession frequency, and we would be able to drive spin rotations. And so these are the rotations that you see here. They are not beautiful, but we were very happy to see them at the time, because it was the first time that we could really see coherent rotations of a single spin in these systems. Since then, our field has progressed. This early data was taken on gallium arsenide devices, and it was convenient because these gallium arsenide structures, different from the silicon structures here, there was at the time already a well-established technology. Lots of mesoscopic physics had been carried out on that platform, and we got going very quickly. However, all the gallium and all the arsenic atoms in the universe carry a nuclear spin. And as much as I like spins, these spins interact with our electron spin. And furthermore, despite the low temperatures and magnetic field, the nuclear spins actually are far from in a pure state. They are in an almost random state. And every time you try your experiment again on the next shot, the nuclear spin orientations will be slightly different. And it becomes a source of dephasing, this unpredictability. And you see it here, right? So the T2 star, this is a Rabi oscillation, right? But if you just let it freely evolve in a Ramsey-type experiment, the dephasing occurs in tens of nanoseconds. So a real limitation. But it was clear that if we could do this experiment in silicon, where only 5% of the atoms have a nuclear spin, or better in isotopically enriched silicon-28, things should look a lot better. And they did. Here's data from the Zurich group at UNSW by Menno Veldhorst, who is now my colleague at QuTech in Delft. And phenomenal, beautiful oscillations, almost no decay visible. The T2 star increased by 4 orders of magnitude compared to gallium arsenide, just by switching materials. So this really gave a big boost, I would say, to our field, also to my own belief that this actually could go somewhere. Now, in these experiments, like I said, we drive the spin in the most conventional magnetic resonance way by oscillating magnetic fields, right? From the oscillating current, Ampere's law, you get an oscillating magnetic field. It was also clear to us that having these sort of clumsy wires next to the qubits, we would not so easily see how to do that on large arrays and so on. And so we began thinking as a community about different ways of controlling the spins. And one of the ideas that existed was, well, can't we just apply the spin directly by applying an electric signal? And of course, electric signals don't talk to spin, but in the material, in the host material, in this case gallium arsenide, there is intrinsically spin-orbit coupling present. And as a result, if you now apply the drive not to this microfabricated wire to produce an oscillating current, but instead you add the drive, the AC drive, to the DC voltage applied to a gate that is already there. You don't need anything in addition. What's going to happen is that the AC drive will wiggle your electron position. And because of spin-orbit coupling, now this motion will lead to an effective magnetic field acting on the spin. And because the motion is oscillatory, also the effective magnetic field oscillates. And so, once again, you can then go to a spin resonance condition. And it worked. Again, that's data in gallium arsenide, all days, first time we did this. And in the meantime, in silicon, this can be done with really high fidelity. 3 nines are completely, are kind of routine or standard nowadays. In some cases, 4 nines, even on simultaneous rotations here from the Tarucha group, have been achieved. And that's actually the method that we use in our lab, although also the first method continues to be used, and you'll hear about it also from Michel, I think. Now, in the gallium arsenide sample, we used intrinsic spin-orbit coupling. In silicon, intrinsic spin-orbit coupling is weak. And so we introduce a piece of cobalt sitting on top of the gate that produces a local field gradient. You see it schematically here, right? And if you now wiggle your electron inside this field gradient, then obviously the electron will experience an oscillating magnetic field once again. If you design things right, then the oscillating magnetic field is orthogonal to the static field. It gives you a magnetic resonance condition, and you can drive spin rotations, like seen in this beautiful chevron pattern. So that's single-qubit operations, how we do them. The two-qubit operation is controlled by gate voltage pulses. Pulses applied to the electrode that controls how well separated the two quantum dots are from each other. And so basically by applying a gate voltage pulse, you can lower or raise the potential barrier between adjacent spins. And if you allow the barrier to come down, the wave function of the spins will begin to overlap. You know, they'll just penetrate through the tunnel barrier, begin to overlap. And when that happens, an interaction will act on the spins. It's not a dipolar interaction, it's an exchange interaction. And it will result literally in an exchange of the two spins as a function of time. This was seen for the first time at Harvard in the Marcus lab. And once again in gallium arsenide, short-lived dephasing or short-lived coherence. In this case, not only because of the nuclear spins, but also because of charge noise. And we then learned how to move to a sweet spot where charge noise has less impact. We transitioned to silicon-28. We understood how to better shape the pulse. And using this, or doing this, several groups, including our own, have now achieved gate fidelities, two-qubit gate fidelities, well over 99%. In fact, based on the quality factor of the oscillations, for quite some years I felt it should be possible, but as we all know, it then takes a really a dedicated effort, to make it happen and show it conclusively. So that's good. It's not a single experiment on one lucky day and in one lucky sample across the world. These high fidelity gates have been implemented, and the list is in the meantime already longer. So putting things together, here we realized a six-qubit device. This is now published a few years ago already. In a way, it's still the state of the art in the sense of how many qubits could be fully controlled and so on, universal control over all the spins. And so here you see the finger gates that define this potential landscape where 6 spins are confined side by side. And you see on top here a piece of cobalt, again, to produce a field gradient. Actually, in this case, we use the field gradient for 2 purposes. One is to introduce this artificial spin-orbit coupling to drive spins. But also, this micromagnet is designed such that the local magnetic field, the total local magnetic field at the 6 positions, is different from each other, and this then allows individual addressing of the spins. And so here you see Rabi oscillations of the 6 spins, taken one at a time. They are not rescaled, so also the readout and initialization fidelities are very high here, around 99%. Single-qubit gate fidelities across the device, 3 nines roughly. And we didn't benchmark the 2-qubit gate, but we did benchmark the Bell states. They were, basically 90 to 95% fidelity. And what was important for us is that this was a number higher than what we achieved a few years earlier on a 2-qubit device, where it was 86 to 90%. So we have a larger device with better control, and of course that is, in general, the path that we need to be on as a community to move forward. Since then, we have performed several other studies on this device, and I'll show just one here where we programmed the 6 spins to go through the steps of a protocol that allows you to study a quench. So it's basically studying quench dynamics and looking at the Loschmidt echo, the return probability as a function of time, starting from this sort of individual, Hamiltonian that acts on each spin at a time, and then transitioning to a transverse coupling Hamiltonian abruptly. So this is, along a linear array. Of course, I already mentioned we like to explore how this works in 2 dimensions, and here you see that in a 2-dimensional array, 2 by 2, the smallest 2-dimensional array in silicon germanium also, again with a piece of cobalt to separate the resonance frequencies, we can have quite beautiful chevron patterns for all of the 4 spins, and these patterns correspond to the coupled evolution between neighboring spins, and as you can tell, we can control the coupling strength through the barrier amplitude as expected. So this is good, like we're moving along. Now on the same device, we did something different. We tested a different way of controlling the spins, not using magnetic resonance. And to do that, we lowered the magnetic field. We lowered the magnetic field so much that it would pretty much cancel the magnetization, the stray field from the micromagnet at the dot locations. So they largely offset each other. And what is left is a local magnetic field at the dot locations, which is very much inhomogeneous, in space. And therefore, the local quantization field differs by quite a bit if you move from one quantum dot to a neighboring quantum dot. And the way we then will try to use this is by starting off in one quantum dot, abruptly moving to another quantum dot where the quantization axis is tilted, allowing the spin to evolve along or around this tilted quantization axis for the, controlled amount of time. Go back, allow it to evolve, and you can do this, 2 times or so. And if you do this in the right way, you can perform arbitrary rotations. You can do x90s, y180s, anything that you want. Actually, what is curious is that only many years after I read the seminal paper by Loz and DiVincenzo, I realized that this is actually what they had proposed. Coming from my NMR background, I was so focused on magnetic resonance as the one and only way to control spins that I didn't think of it more. And even reading the paper, I had always thought, we need to do magnetic resonance. It's great, it's strange. But actually, that's what they had proposed. You see the beautiful drawing. It's very realistic because the electrons or the quantum dots are not circular. And it actually works. On this device, the gate fidelity that we could achieve with this method using the tilted fields was the same as with the typical resonant control. And so, I think it actually could be, well, certainly we're going to explore that further. Maybe it's going to be the way of the future, let's see. One advantage is that, ballpark estimates would tell us that the power dissipation is about 100 times less than in a typical 10, 15 gigahertz, drive experiment. And so, yeah, maybe crosstalk is more localized and so on. So we'll see. But I think this is, well, something that for sure we're going to pursue more and see how well this can work. Let's see. Maybe I'll skip this one. Also, I love it. 8 spins, all participating in coherent time evolution. Here you see a gallery of some devices made and measured around the world. This is from HRL, from Princeton. This is from Intel. This one I like in particular because the way that this device is made is, using fully, really using the standard advanced manufacturing methods from the semiconductor industry. For those that know about these methods, there is no electron beam lithography, there is no liftoff. So this is really optical lithography. It's using the EUV $100 million tools from ASML. It's using etching and so on. And the result is that the patterns are extremely reproducible. I think the qubit quality at the moment is comparable to the better qubits from academia, not yet better, but hopefully that will come over time. This is from Menno Veldhorst in Delft, and this also is one that I like also from Menno in Delft, because in this case there are actually shared, the idea is shared control. So just like in a computer screen, we have word and bit lines to address pixels. The idea here also was to use word and bit lines to address the qubits, and they showed some, they couldn't achieve full control of it, just like it wasn't done on any of the other devices, but some of the basic functionality was already shown. And this can be a route to more, to scaling in the end, and managing the number of wires. So talking about scaling, I think that in our community there is a common understanding that we will want to increase the size of these qubit arrays, of these quantum dot arrays, and that's happening. At recent conferences, Intel and HRL show devices with beautiful images of, arrays in 2 dimensions. It's happening, it's coming. But we also think that there will be, for many reasons, a practical limit to how large we'll choose to make these local arrays. And that for scaling beyond, we will have many replicas of those arrays, all on the same chip. So the entire picture you see here is one chip, not several chips wired together, no, one chip. And on the chip, we'll then have links to connect these registers together so that we can distribute entanglement, we can basically use them as one large quantum processor. Also, we imagine that in order to overcome one of the most important practical challenges in scaling, which is the wiring bottleneck. The wiring bottleneck means we now use 1 or 2 or so, let's say 2 wires per qubit. It works for the moment, but it will not be possible to bring 1 million wires to a small chip to address 1 million qubits. And so what instead we could do, and we're exploring that, is to have some embedded classical functionality to, for instance, route signals, perhaps even generate or process signals on the chip on board. And so that's also a research direction that's happening. I will not have time to talk about it, but I do want to tell you about our progress in achieving these quantum links. And we follow 2 methods for doing that. The first is to literally take an electron and move it across the chip. So shuttling. It's an idea that existed for many years in the Eintrap community, also the cold atoms with Rydberg, with optical tweezers are benefiting from that. And also here, we can imagine moving electrons across the chip, to connect these registers together. And we began testing it in a device similar to the 6-qubit device I showed earlier. It's a different fridge, different device, slightly adapted design. And the first method we explored was to empty this array, put an electron in, and push it from one quantum dot to the next using the gate voltages and back. Do this repeatedly and test how well this phase is preserved. And the phase flip probability per hop, or the fidelity per hop, was pretty good, 3 nines, more than that, which looks like a good number, but it's not good enough if you consider that, to cover a distance, the errors will accumulate to numbers that you're not so happy with anymore. So then we tried a different method on the same device. And by the way, what you're looking at here is how the frequency of the qubit changes as we displace the electron along the vertical axis. So what you see is that at some point you have a fixed frequency corresponding to side 2. Suddenly you switch to the frequency of side 3, side 4, and so on. Now in this other method, what we do is not to make the electron hop between static dots, but to make the dot itself gently move and carry the electron along. So we call this conveyor shuttling. And you see that indeed the frequency now varies quite smoothly as we take our electron through the gradient magnetic field from the micromagnet as opposed to abruptly. And it turns out this actually worked a lot better. The phase flip probability was 10 times lower, and a combination of numbers that I like a lot is that we performed randomized benchmarking to test the fidelity after moving the electron back and forth in this device over a total distance of 10 micrometers. That took less than 200 nanoseconds, so it's quite fast. And the fidelity at the end was 99.5%. And that's a great combination of numbers, because 10 micron, that's maybe the upper range of what we imagine. I mean, maybe 20 micron, but it's a good number. And so that actually makes us optimistic that shuttling can be a component of future spin-based quantum processors. And I actually believe now that in a few years' time, when we go to conferences, from our community, you will see shuttling performed just as routinely as a Rabi oscillation or a two-qubit gate. That's what I think. That is just going to be part of our toolbox. Yes, Michiel.
I'm curious, in this experiment that randomized benchmarking and shuttling, what's the order? Do you do a gate, shuttle, or?
Yeah, so I don't have the sequence here, but basically, yes. So a gate and then 10 micron, a gate, 10 micron. Gate.
Has there been an analysis of the interconnect energy cost?
So
This is, of course, a big issue
yep.
in classical electronics, especially AI and things like that.
So what we have done is to test, of course, how large the amplitude is of the voltages that we need to propagate the spin, and we at some point begin to see some heating effects. They are at the moment weaker than for qubit drives. So it's because the frequencies are lower, and that helps to have less dissipation. The last word has not been said, and I don't think we can claim that we have done a thorough quantitative analysis, but that's kind of where we're at. So this was now shuttling within this device, and we've also fabricated devices. Oh, I forgot to add the references of other groups that have been working on this, like Lars Schreiber in Aachen, where you construct a device which has a channel that's 10 micron long. Because one thing is to see an effective 10 micron, but what if you really cover 10 micron? Do you get the same result or not? And that's something important to test. And so you see here how these conveyor channels are constructed and operated. And what's important is the number of wires. So there are 4 wires that are used to drive the electrons forward. And the way this is done is by applying 4 phase-shifted sine waves to the gates, right? A voltage or a sine wave to the 1st, 5th, 9th, and so on. And then phase-shifted to the 2nd, 6th, and so on. And if you do this, you can produce a traveling wave potential that carries your electrons. And depending on the phases, you can choose to propagate left or propagate right. So this is ongoing. We got some initial results that we can carry our electron along, but it's kind of preliminary still. And so based on these successes, we're beginning to imagine that shuttling can be used not only to connect registers to each other, but also to increase connectivity within registers by taking any 2 electrons, moving together to perform a 2-qubit gate, even if they were not nearest neighbors. So this would be in an array where we don't occupy all the sites. It's a little bit sparsely occupied, yeah, so that there is room to move the spins around and then create arbitrary connectivity. And the other question we are asking ourselves, if we can carry these electrons, in these conveyor minima with high fidelity, can we perhaps also operate on the spins, on these mobile spins, instead of operating on spins in static dots, operate directly on the spins in the conveyor potential? And we began to test that. And so here we move, still in this old device, we move 2 electrons in their conveyor minimum towards each other. And you see how the frequency of one and the other kind of smoothly varies. But as they approach each other, the lines split because of the interaction between the spins. And this interaction we can use to perform 2-qubit gates. And already in this first test, the 2-qubit gate fidelity was 99%. And I think there is really room to push this further. We've used this 2-qubit gate in a conditional quantum state teleportation protocol. Let's see, maybe for the sake of time, I will not go to take you through the details, but it's a pretty nice, sophisticated experiment. In the end, the upshot is that the teleportation process fidelity was 87% estimated here. So we can perform 2-qubit gates on spins that are in these conveyors directly without transferring to static dots. What about single-qubit operations? Maybe we can also do that. Remember, the way that we control our spins using electric fields is we wiggle the position inside the quantum dot, where it's actually tightly confined, but we kind of wiggle it by a little bit on resonance with the spin transition to drive the rotations. The PETA group tried to make the electron cover a larger distance by making it hop between 2 dots, and that worked, but the quality was not great. Actually, I didn't explain why the shuttling works better in this conveyor versus with hopping, but it's the same reason why this in the end didn't work so well. But now, what if you take your conveyor and you move your electron on resonance with its own Larmor frequency in this transverse field gradient. And so we tried that, and that also works. The pattern looks a little bit skewed. That's not because there is anything wrong. It's really what we should expect. It's got to do with the technicalities of how we drive this. And already here, the X90 fidelity was above 3/9. It's actually a lower bound because well, I'll skip the details. And the Z control is almost perfect because it's just idling. You just wait for a little while. So yeah, who knows? You know, these are all new ways of thinking about our system that can open up new possibilities and then, in the end, maybe make it easier to scale. That's what we're testing. Coming back to the increased connectivity, here is a device that's been called for maybe a month or two or so, well, not that long. And what it's designed to do, it's a bit complicated device. You see the micromagnet here. And then there's a window in the micromagnet. This will produce, you know, again, a gradient in the local magnetic field. You see here all the finger gates. And then you see 4 more gates. We'll use, by the way, what I didn't discuss at all is how to read out the spins. If you like, I can answer questions at the end. But so we're going to read out here at the end. Everything we do, all the data I'll show you, is done by probing the system here at the end. Now, inside this channel, we will move spins around using this conveyor principle. We call that a bus. And then there are 4 bus stops, stationary qubits. So the idea is we transfer an electron from the reservoir into the conveyor channel, transfer it to the bus stop, and then we can transfer another electron to the next bus stop, take this one, move it here, and so on. That's kind of the idea. Okay, does it work? Here is preliminary data where we take an electron, move it next to one of the bus stops, probe the spin resonance frequency, and then tilt the potential so that, you know, the electron will be transferred from the bus onto the bus stop. And that's what's going on along this axis here. And then you see as a function of time an oscillation. And so the point is that if we transfer our electron from here to here, you would expect a change in the local field and therefore a change in the frequency. And so that's what we see, and that's, you know, we take this as evidence that indeed we've loaded our bus stops one at a time. And then after we've loaded the bus stop, oh, what happened here? Okay. All right. Okay, after we've loaded the bus stops, we're going to bring a second electron from the, into the conveyor and position it next to an electron in one of the bus stops and test if we can see evidence of the interaction between them. And the experts will recognize the so-called fingerprint plots. I will not go through the details here, but indeed, we are able to see the interaction between the spins in the conveyor and in the bus stop. We have data now for 3 of them. The first one, there is more interaction with the readout region, but that's hopefully coming soon. So that's kind of where we are with this experiment. It's in progress, but I think it will open a lot of opportunities to think in new ways about how to use these quantum dot systems. So how much time do I have, John? 7 minutes. 7 minutes before the questions. Okay, great. So then I have time to tell you about a different method we have tested to control or to build quantum links to connect these registers to each other. And in this case, we use a superconducting resonator to connect the spins together. Superconducting resonators, of course, have been studied with tremendous success in the superconducting qubit community, and so we borrow all of the concepts that have been developed there and basically more generally in cavity QED. So what we have is a double quantum dot on one end, a double quantum dot on the other end. In between, we have a piece or a line made from niobium titanium nitride. It's about 100 nanometers wide. It's fairly thin. And it's 200 micron long, roughly. And the endpoints of this resonator are galvanically connected to one of the quantum dot gates here. We will occupy each electron, each double dot with one electron. the first natural idea would be, oh, okay, we're going to use this resonator, which produces electric and magnetic fields, and we'll couple the spin to the magnetic field. But you quickly discover that that interaction is far too weak. So we go back to this other way of talking to spins through electric fields. So we'll have an electric field component from the cavity photons, talk to the spin, once again, because of these pieces of cobalt micromagnet that produce a local field gradient. To maximize the coupling, because here what we'll be after, in the end, is to have a coupling between a single localized spin and a single microwave photon, which is larger than the spin lifetime and larger than the resonator decay, the cavity decay. And so to achieve that, we have a resonator made from a high kinetic inductance material so that we get a large impedance resonator, maximize the electric field locally. What happens then is that the position, the dipole of the electron in the double dot interacts with the microwave photon. Because of the field gradient, you indirectly get a coupling between the spin and the photon. Several groups have now seen the strong coupling regime between the spin and the photon with some results. I don't have the slide here, achieving very strong coupling regimes, and also Pasquale Scarlino, maybe later in the week, will show you his results on that, which are quite amazing. Now here, we'll then have the spin coupled to the photon, another spin coupled to the photon, and the idea will be to achieve also indirectly a coupling between the two spins. And it actually works. So what we'll do is bring one spin in the excited state, leave the other in the ground state, and then, bring the two spins on resonance with each other, like here, but detuned from the cavity. So this is a dispersive interaction between the spins. And as a result of the dispersive interaction, we see indeed that the spin populations are exchanged between two individual electron spins separated on the chip by 200 micron. And the interaction is actually very fast. It's just tens of nanoseconds periods, despite the distance. In conventional experiments, like I showed the two-qubit gate before, the two spins are 100 nanometer apart. Here, they're 200 micron apart. Still very fast oscillation. It is quickly damped. This device is suboptimal in many ways, and if you put together improvements kind of selectively from published individual works, and you manage to put it all together, then a two-qubit gate fidelity of 99% should be feasible. Of course, one thing is to say that, another is to show it, but that's kind of where it could go. So these are I-swap oscillations between the two spins. Next, in work that's still unpublished, we test what happens in the resonant regime. So now we go to the regime where the spins are become resonant with the photon, both or one at a time, and then you can get vacuum-Rabi oscillations. So here, these oscillations correspond to energy that is coherently going back and forth between one of the spins and the microwave photon in the cavity. So here the spin is excited, here the spin is in the ground state, but one quantum of energy is in the resonator. Here that quantum of energy is transferred back to the spin, and so on. We can do this for one qubit, for the other, and we can also combine it and then perform a vacuum-Rabi oscillation on one end, but we probe it at the other end because we transfer the population through the cavity from one to the other end. And so in this way, we can concatenate things. So yeah, we'll see also where this can bring us, but that's kind of where we're at. As a final piece, I want to show you experiments. I don't know that we'll really see them as the best way of connecting these registers to each other, but it fits conceptually a little bit in the same framework. What we're testing here is how we can transfer a spin excitation along a chain of coupled spins in a quantum dot array. And the way we do this is by a combination of methods from digital, quantum computing, single qubit rotations, two-qubit gates, and so on, and then analog evolution where you let the full system evolve under its Hamiltonian, and the Hamiltonian then contains the couplings between all the spins, which are individually adjusted and calibrated. And so by doing this, we can study quantum walks, how these magnons, these spin excitations, propagate through the array. And we can do this for different topologies. So in this case, only one coupling is activated, and you see that the population oscillates between these two sides. Here, there is another coupling active. This is brought in an excited state, but it's not coupled to anything, so the excitation stays. Here it can go around the ring, and depending on, basically what you see in these three plots is how the competition between the couplings that like to propagate the spin excitation through the device and disorder due to inhomogeneity in the local G factor, and therefore disorder in the spin splittings, how these compete and can either allow or not allow spin excitations to propagate. This is kind of similarly conceptual to many-body localization, and we look forward to doing such studies on larger systems in the future. This last experiment fits in a research line that I won't have time to cover, unfortunately, on analog quantum simulation, where these quantum dot systems are used to directly emulate Fermi-Hubbard physics. The electrons are fermions, they're at low temperature, low compared to the relevant energy scales. And it's a super flexible, versatile system that allows us to study a wide variety of physics, from itinerant ferromagnetism to excitonic physics and so on. So we'll continue that. Wrapping up, I think that we are now on a trajectory where we can control with high fidelity, with higher and higher fidelity, increasing numbers of qubits. That's a good path to be on, and we're testing various ways of coupling spins at the distance, of moving them around to change arbitrarily connectivity and so on. Nothing is easy here. I want to be clear, and as always, there is a lot of hard work behind it, but I think we're, as a community, on a good trajectory, and I'm hopeful that we'll continue to make good progress. So I really like to acknowledge the contributions of the group. This is a picture in the Dutch mountains, as you can see, very tall mountains. Also, I'm very grateful for many collaborations for many years that have been very helpful and important to this work. Thank you all.
Questions for the speaker?
Thank you so much for lovely... Is it working? Okay, thank you so much for lovely talk. I actually have a question because you showed some spins with interaction. So do you have already a way how you control this interaction on just simulation model, and how big this exchange coupling is supposed to be in your case? Just out of curiosity to step in for physical stuff.
Yeah, so typically the way that we calibrate the interaction is by looking in the time domain at oscillations pairwise. And then we have methods and separate, also publications about how to account for crosstalk, because you can calibrate a vertical pair and then independently calibrate a horizontal pair and the next one. And the gate voltages will induce some crosstalk where what you've just calibrated will be affected by what you're next calibrating. And so by an iterative process, which is quite systematic, we can then dial in independently all the exchange couplings with, what
how
type of...
much in EV, just out of curiosity?
What is the value?
Yeah, just...
So the J, let's see, so we can... so a few micro EV is sort of the upper value, and then we can switch off by orders of magnitude.
But technically you do like with nearest neighbor only, yeah? You don't go any further on the chain.
So typically we use nearest neighbors. However, we've also done studies where we look at an effective coupling between two spins with a site in between. And then you get like a co-tunneling. Well, you get a J coupling induced by co-tunneling instead of by tunneling. So co-tunneling instead of tunneling. So it's a higher order process, and that can also happen. Also, I want to note that if you build a triangular array, then
You have frustration.
Well, you can get frustration, but I also want to say that if you then have your diagonal backbone, then these couplings become also next nearest neighbor couplings. So there are lots of ways to play with the geometry and the connectivity.
Okay. No, I'm just curious how you keep it in control and just,
Yep.
yeah. Thank you so much for response.
Thank you. There's a question next to you also. Yeah. Well.
Thanks for the interesting talk. My question is about scalable sort of architecture. You outlined several approaches, how you want to increase the number of qubits. But sort of what is your vision for, say, logical qubit and coupling to the error correction code? Where is this going?
So let's see. So basically, I want to say two things. I think we used to start reasoning from the surface code. And in a two-dimensional array, you can implement that. But with the shuttling, I think it's really worth to design codes that are adapted to the specific connectivity that we can achieve. And so I'm hoping that these results will encourage theorists to think about this. But I can also tell you how, in this device, one can implement the equivalent of a surface 7, for instance, because you have 4 data qubits that can be here, and then your oscilla can combine one after the other, form a 4-way or 2-way, as you choose, parity measurements. So yeah, that's kind of a brief answer. There's much more to say.
Yeah, maybe following up on that, and since you planted the idea of asking a question about measurement that I will never resist, can you comment on the ability to do quantum non-demolition and mid-circuit measurements? How challenging is that?
Yeah, okay, so let me first perhaps then take the opportunity to explain how we read the spins in the first place. And so there are several ways of doing that, but in most of the measurements that I've shown, what we do is to compare the spin in adjacent sites using the Pauli exclusion principle. So basically, if the two spins are in a singlet, they can come together on the same site. If they're not in a singlet, in one of the triplets, they are forced to stay in separate sites. And then that means that an electron is displaced or not, depending on the spin state. And what you can see on the side of this array is a larger additional quantum dot. We will tune it to a condition where the current through it is extremely sensitive to the electrostatic environment and can easily pick up the motion or the displacement of an electron from one site to an adjacent site. In practice, this measurement, sometimes it differentiates singlet from triplet. Under different conditions, it effectively is a parity measurement. And yes, it can be, there are also variants that are Q and D by themselves. And in addition, what you can do, of course, like always, and that's also been done in our group and elsewhere, is to perform CNOTs for quantum non-demolition measurements and repeat measurements. So that's also something that's been tested and that works. The last thing I'll say is that what I see as a point that needs more attention, and we are going to focus more on it, is to improve readout. At the moment, most of the experiments work with readout is relatively slow, and for instance, in the teleportation protocol, of which I skipped the details, our readout is slower than the dephasing time, and so that's why we did this sort of post-selected teleportation, like in some photonics experiments.
Thank you.
So very nice talk. I have a question about scaling. So imagine you have a 2D array, and eventually your micromagnet is going to be giant. So how do you solve the frequency crowding issue?
Yeah, so in the two-dimensional arrays, I think that one would need a combination of local addressing by gradient magnetic fields and spectral addressability in combination with the spatial selectivity from your control signals. So if you deliver a signal to one of these gates, it will also impact the neighboring dot and a little bit the next neighboring dot, but that crosstalk does fall off rapidly, and I think a combination of these two is probably what would be needed. The other is that in addition, or as an alternative to having one large micromagnet, we've also, and we're not the only ones, been thinking about local nanomagnets. for spatial addressing, and that can also be a way.
Thank you.
Let's do one more question.
John, I have a question.
Looks like there's one over here.
Thanks for the nice talk. My question is on, so what is your vision and the best resource for memory or storage of this information in spin qubits?
Yeah, so I think, in basically the spins themselves have a good memory in the sense that with dynamical decoupling, the decay times can be really long. So in some architectures, people imagine having some hybrid with long-lived qubits for memory and fast qubits for operations. Then, of course, you pay the cost of transferring. It could be a way forward. I don't know. If we wanted to go that way, probably what we would do is start using engineered nuclear spins nearby, and you can hear from Michelle Simmons in a moment on how that combination can be very powerful in their platform.
So, Lieven, let me ask you a question about something that I have concluded. I want your opinion. So my conclusion is that this micromagnet thing basically nullifies the main advantage of semiconductor qubits, which is scaling up. There is never going to be a million qubits this way. And I'm interested in integer factorization. That's the only problem I'm interested in. And so with micromagnets, it's not going to happen. Then to my somewhat pleasant surprise, I found out, at least in the United States, Intel, HRL, Jason Peta, all believe the same thing, that you have to find some other platform. So what do you think of exchange only?
Yeah, okay, so I think one can disagree about the micromagnets, and in particular, like I said, nanomagnets, maybe it could actually be perfectly fine for scaling. Exchange only for everybody. This is a qubit encoding where the qubit is not given by a single electron spin, but by the collective state of 3 spins. So it's an 8-dimensional space. You select 2 of them as a qubit. The benefit is that you can get universal control by only manipulating the exchange coupling between neighboring sites. The downside is that is the overhead. So you need several exchange evolutions for the single qubit gate. You need 10 or 20 for the 2-qubit gate. And then the question will be, what is the best compromise in the end, right? So the 2-qubit, will this approach give you good enough fidelities to in the end be fault-tolerant? So,
but are people in QuTech, are you thinking about it, or you are not looking at that at all?
We are thinking about it. Our theory colleagues locally, Maxime Bachrus and so on, and Stefano Bosco have also been publishing about it, and we discussed with them. There are many variants of this exchange only. So it's on our mind. We have not started any concrete experimental activities. And I think as an alternative, so one of the other advantages that Jim Clark from Intel has been trying to convince me of for many years is exchange only. It uses only baseband control, no microwaves, so less heating. I show you several ways that we can achieve also baseband control for single spins. And by the way, maybe we'll close here with a little anecdote. I attended a conference at Yale celebrating, what was it, 20 years of circuit QED, a year and a half ago. A very nice conference, and I remember people like Michel Devoret stating with much emphasis, avoid DC like the plague. So he's of the complete opposite opinion. No DCs, no DC voltages, no DC control signals. Everything needs to be microwaves. Okay, so we can argue about it more.
Okay, let's thank Lieven again, and then we'll head to coffee.